Okay, part B, determining an inverse variation, is a build on of part A. Simple steps. We're going to use the general function from the inverse variation, y equals k divided by x. We're going to substitute for x and y. We solve for our k, and then we create the function by substituting k back into the general function, the general form. Okay, so here we have, suppose x and y vary inversely in x equals 4 when y equals 12. Okay, so it tells us that we're using inversely, so we know we're working with y equals k divided by x. They give us our x and they give us our y. So we're going to substitute these in and solve for k. Does that make sense? So we have 12 equals k divided by 4. So I multiply both sides by 4. So k equals 48. So our function model is y equals 48 divided by x. So just based on what we have, if we're looking at 4 and 12, let's say 4 is here, 12 is here. This graph, it's decreasing over time. And the reason why we know it has to be decreasing is because how else am I going to come down? So the graph is doing something like this. And we'll dive deeper into what the graph is doing and how it's moving here in a little bit in the next section. All right. So then example 2 is wanting us to use the function from example 1 to find the value of y when x equals 10. So we have our function model, and our function model is y equals 48 over x. They give us our x value. So y equals 48 over 10. And I simplify that down to 4 and 8/10. Easy enough once you have the function model, right? Still good?
So I'm gonna assume that instead of it being.
All right, so here's your try. So you have the information, and this time you're going to find the function. You're going to use the function to find the value when x equals 5 and to find the value when y equals 5. So I'll give you a moment to do that. All right, so let's see how we did. So it told us inversely, and it gave us our x equals 8 and our y equals -7. So we're working with y equals k divided by x. So we know that our k equals x times y. So that gives us 8 times -7, which equals -56, right? So our model is y equals -56 divided by x. Agreed? All right. Done. And then we're going to use the function to find the value of y when x equals 5. So y equals -56 divided by 5. You should have got -11 and 2/10. Yeah.
I didn't go that way, but I still have the same answer.
Cool. And then we're going to use the function to find the value of x when y equals 5. So this time we have 5 equals -56 divided by x. Then multiply by x. And divide by 5. Oh my goodness. You get a -11.2 again. Okay. All right, so notice how we have a point at 5, -11.2, and we have one at -11.2, 5, right? So graphing this, it's not a parabola. These two lie in two different quadrants, don't they? I have a positive and a negative, and a positive and a negative lies in quadrant 4. And I have a negative and a positive, and that lies in quadrant 2. So we have something happening in 2 and something happening in 4. So what's happening is the graph is doing this. So the graph is doing this, and we're not crossing x equals 0 because where's x located? In the denominator, right? And can you have a 0 in your denominator? No, we can't. Okay. And mathematically, if I'm dividing something and I'm continuously just dividing and making it smaller, is it going to ever equal y equals 0? No, it's just going to keep getting smaller and smaller and smaller. So which part of this graph I'm talking about depends on the situation. So in quadrant 2, I am decreasing in time, but increasing in, not time, decreasing on my x's, but increasing on my y's, right? In quadrant 4, I am increasing over time and decreasing, not over time, over x and decreasing over y. So it just depends on what the situation is and how it pertains. So we're going to look at a real world situation so that we can see which graph, which part of the graph, which quadrant will we focus on. Does that make sense? So in our last example is our real world example. Oh, after a major storm, your math class volunteers to remove debris from yards. The table shows the number of time, t in minutes, that it takes a group of students to remove the debris from an average sized yard. So looking at our table, if the number of students, if there's only one student, it would take them 225 minutes. If there's 3 students, it would take them 75 minutes. 5 students, 45 minutes. 14 students, 16 minutes. So looking at this, we can conclude that the more students, if we increase the number of students, it'll decrease the amount of time it takes, right? So we're looking for an increase over a decrease situation. And it says, what function models the debris to clear the debris from the average yard relative to the number of students who do the work? Well, because of this, we know that we're looking at y equals k divided by x. We know that it's an inverse or possibly an inverse relation. So to find our k, we're going to take each one and multiply by our x times our y. So we have 1 times 225. We have 3 times 75. We have 4 times 45. And we have 14 times 16. This gives us 225, 225, 225, and 224. Now, this is a real world situation. So the fact that it's just slightly off, that's irrelevant. We can still take the average of this or kind of use our common sense to know that our k value equals 225. Do we see that? So my function model would be y equals 225 divided by x. Pretty simple, right? Okay, and because of that, I know that I'm working only in quadrant 1. And so my y values, the time it takes is going to decrease the more students that there are. So my graph ends up looking like this. All right, so that concludes part B.